we're going to take a look at some textbook examples, some not me just showing you the relationship between geometry and calculus, and start running through a whole bunch of examples that you're going to see similar to what's in the book or on an AP test. So how do you find, now this section is volumes of solids using disk washer and cross section. We are going to do some examples of all three of these today. In general, how do you find the volume of a solid? Now there is a shell method for finding volume, but we do not need to cover that. That's beyond the scope of the course. So we're slicing our solids into disks, washers, or cross sections. In general, this means that we're finding volume by a definite integral from A to B, and that integrand is going to be an area formula. Sometimes the area of a circle, sometimes an area of basically two circles, a big circle with the small area in the middle subtracted out, forming a washer, and sometimes a cross-section of prescribed shape, or actually just a formula being given to us. So in general, volume is the definite integral between A and B, and your integrand is going to be an area formula, and then that's the area of the base of a prism. And then there's some height to it, which is going to be in the form of either a delta x or a delta y. I'm going to write just, dx here, but you can be integrating with respect to x or y. That'll be dependent on your problem. So it says here in example 1, we're going to use the same three functions and work out three different problems, all of which are pretty varied in their algebraic work. So we're going to take the function of y is equal to the square root of x. And let me just draw that over here. A rough sketch. So we're going to have y is equal to the square root of x. We're going to have y is equal to 0. And another equation that's going to create a bound region within a quadrant or between two curves. We're going to have another curve of x is equal to 4. And we're going to take this region and we are going to rotate it around an axis for these first three problems, creating a solid that we're going to find the volume of. So we're taking this region for the first question, and we are going to revolve this region. I'll have to redraw this over and over again, and revolve that around the x-axis, or around the line y is equal to 0. So it's not that important for you to be able to visualize the solid that you're finding the volume of. What's most important is you can find the area of the cross-section. But this is a sideways parabola, and I'm missing a disk out of this model. But we're going to be finding the volume of this bowl. Whether it's like a glass that's holds something, or the front of a nose cone of a plane, maybe whatever the application is. This shape where the sides are formed by a parabola, we're going to find the volume of that by finding the volume of a bunch of little disks that have an area defined by, a circle. And then there's going to be a little bit of height, a lot of delta x's or delta y's. When you're finding volumes of solids that are formed by revolution, which is basically about 2/3 of the problem in this section, you're going to be needing to think about representative rectangles. Well, basically, the number of rectangles are going to go to infinity, right? We talked yesterday a lot about all we're doing is applying that first fundamental theorem, the definition of a definite integral that you learned back in chapter 4, and the number of those rectangles going to infinity. So these rectangles are going to have a little delta x. The representative rectangles, or basically what I'm going to focus on saying the radius of our circles when we spin things and get cross-sections which are circles, those radiuses are always perpendicular to the axis of rotation. Those representative rectangles are going to be perpendicular to the axis of rotation. So because our axis of rotation is a horizontal line, we're going to have a lot of small delta x's. We're going to set up an integral with respect to x. And even though I just said it's not super important to actually be able to visualize the shape you're finding the volume of, let me just take a minute here because it's not too hard to draw. This one anyway. And that is the cone, that sort of bowl shape that we're going to find the volume of. Does that make sense? Okay. If the area that you're spinning touches the axis of rotation throughout the entire domain of interest, your solid will not have a hole in it. Your area formula, that's your integrand, is just going to be the area of one circle. And of course, we know the area of a circle is pi r squared. So everybody good with that, right? So we're going to be doing a definite integral. Volume is equal to a definite integral from between two numbers with respect to x. Because we are integrating along the x-axis, our lower and upper limits of our definite integrals are going to be values of x. And this region starts at the origin and goes out to the line of x is equal to 4. So we're integrating between 0 and 4. And we talked yesterday about the volume of a prism. And there's this, while this is not a prism, there's a whole bunch of cylinders in here. Now, I'm not going to take a word about drawing that. And that dx or dy is going to be your height. And we just need the area of those cross sections in here, which is going to be pi times the radius squared. So the radius, even if you're subtracting by 0, I want you to key in on that the fact that we are finding the lengths, the radius is the length of a vertical line segment. Just like, recall when we just finished 7.1, when we were finding area between curves, and I emphasized, that you have a bunch of representative rectangles and you need to find those heights. And that radius, that height, is constantly changing. And when you want to find a vertical distance, it's big Y minus little y. I know the axis of rotation is 0. I know minusing 0 doesn't really change or do anything, change the answer or do anything. Addition of 0 is an identity for addition and subtraction. So this is only to get down the process, to get down the memorization of what you need to do. This big Y, all of these line segments are on the parabola or on the graph of y is equal to square root of x. That's the big Y. And the little y is down at the bottom, and that's 0. So you have square root of x minus 0. That's how you calculate the variable radius for each of the disks that you're going to spin, find the volume of, and add all of those up. OK, well, pi is just a constant, right? So the pi comes out. You don't have to move it out, but it's easier. So the pi comes out. We have a definite integral between 0 and 4. The square root of x squared is x dx. And now we're just going to go through the process of solving this. The integral of x to the first is going to be 1/2 x squared. So we have pi times 1/2 x squared with an upper limit of 4 and 0. And now plugging in that value, oh, and if you want to, you can now take the 1/2 out front and say we have pi over 2 times 4 squared. So we're plugging in the upper limit, 4 squared. Now substitute in your lower limit, 0 squared. Make sure you think about that, because when you e to the 0 is 1, the cosine of 0 is 1. Sometimes when we substitute in 0 into a function, we don't just get 0. But in this case, we do. So we have 4 squared is 16, and 16 divided by 2 is 8 pi. We are finding volume, so it's going to be 8 pi cubic units.
We have done this lesson. We did this all Friday.
Great. Thanks to you for telling me that now that we're 10 minutes in. We did all 3 of these. Do you want me to just jump ahead to something else then? I don't want to waste your time. Do you need this? No? Let's do a new one then. Volume of a solid, when you're slicing it up in disk washers or cross sections is the volume is equal to the definite integral from a to b of the area of the cross section times dx. The question that's up on the board is an old AP, very old AP question, and it is the reason why I changed the way I teach finding volumes of solids. And I don't emphasize that you remember and memorize a formula for disk and washer, and then teach non-rotating volumes as a different concept, even though it's in, because it always felt like a different concept until I got to questions like this. Let R be a region enclosed by the graphs of g of x is equal to negative 2 plus 3 cosine of pi over 2x, and h of x is equal to 6 minus 2 times x minus 1 squared, the y-axis, and x is equal to 2. So there's the region that we're going to be working with. For the solid, at each value of x, the cross-section perpendicular to the x-axis has an area given by a of x is equal to 1 over x plus 3. Find the volume of the solid. Who knows what to do with this problem? All of the questions, or nearly every single question in the book, they give you the shape of the cross-section. The cross-section's a rectangle. The cross-section's a semicircle. The cross-section is an isosceles triangle. It's maybe sitting on a leg, a right isosceles triangle. The cross-section is an equilateral triangle. Well, that's great, but if you get stuck on the fact that, I have to create my own integrand, my own area formula, when you get a problem, and for my class, the year that this question came out, it was probably the first time they saw a question about volume that did not give the shape of the cross-section. And to be honest, my kids were kind of like probably disadvantaged because of that. They're telling you what the area formula is. You don't have to make your own up. You don't have to go, oh, the area is a cross-section that's a rectangle. Let me find the base of that rectangle, then multiply it by the fixed height. Or that cross-section's a square. Let me find the distance between the two curves and then square it because that's going to be the length of each of the variable sides. No. The area, every cross-section has an area given by this function. And what is the integrand when you're finding volume by disk washer method or by slicing solids up into slices? Area. So this is the definite integral. The volume is the definite integral of 1 over x plus 3. Now, is this correct, or do I need to rewrite this and integrate it with respect to y and have a function in terms of y? Okay, well now, it does say that you are slicing, you are making cross-sections that are perpendicular to the x-axis. So while this cross-section is not a rectangle, and actually I don't even know what the shape of it would be, but every time I slice it, I'm making a slice that is perpendicular to the x-axis, which means I am integrating, you are integrating with respect to x's. So yes, we're going to keep that area a of x is in terms of 1 over x plus 3. We are recognizing with this statement we're making cross-sections perpendicular to the x-axis that we're integrating with respect to x. Now, if we're integrating with respect to x, we are integrating between two values of x or two values of y? Yeah, of course, it's two values of x. So we have x is equal to 0, and over here to the far right, we have x is equal to 2. So the volume of the solid, which I can't visualize at all because I don't even know what the shape of the cross-section is, plus just trying to visualize it honestly, while kind of interesting, is really a waste of time. We're doing a definite integral between 0 and 2. This question was so easy, but not based on how I taught it that year. I never did one single practice problem like this before seeing this question on an old AP test. And I never emphasized that the integrand is an area formula. So that's why I made the big deal about tying in the calculus with the old geometry stuff and how it was the area of the base times the height. So what does this look like? What integration rule does this look like? I don't like quotient rule, but it's the integral of u prime over u. So we're certainly not going to need to do a u substitution. But if we let u be that denominator of x plus 3, then du, the derivative of x plus 3 with respect to x, is just 1 dx. So we have a u in the denominator and a u prime. Like we already have given a area formula that is in the form of u prime over u. And of course, we know the integral of u prime over u is natural log of the absolute value of u. So we have the integral, we have a definite integral from 0 to 2 of 1 over x plus 3 dx. That's going to yield the natural log of the absolute value of x plus 3 with an upper limit of 2 and 0 as a lower limit. And then we have the natural log of plugging in the 2. We have the natural log of 5 minus plugging in the 0, the natural log of 3. And you absolutely could leave this answer in this format. If it were multiple choice, they might be a little bit annoying and condense this logarithm. Logarithms are what? Exponents. And when do you subtract exponents? When you're doing what with those same bases? Dividing. Logarithms are exponents. And when do you subtract exponents? When you're dividing like bases. So we have the natural log of 5 divided by 3. Zero reason to do that simplification on an AP test. You actually run the risk of losing a point because you did something silly, like maybe you wrote natural log of 3 times 5, or you just completely messed it up. You should not, after the calculus is done, which is this line here, you should stop simplifying your answer and just move on. But if it were multiple choice, you might see natural log of 5 divided by 3. Okay, so let's take a look at a different question. Actually, let's just for review say, for the solid, we're not going to work this out, but we'll set it up. For the solid, at each value of x, the cross-section perpendicular to the x-axis is a, how about a semicircle? Each cross-section is a semicircle. So we'll see if this makes the cut for the video. So we're going to have a cross-section, and that cross-section is going to be a semicircle. So how do you find the area of a cross-section? How do you find, excuse me, that is the shape of the cross-section. How do you find an area of a semicircle? Yeah, this area formula is going to be 1/2 pi r squared. So then what is the radius going to be equal to? What's the radius going to be in general? Or am I just stumping you right off the bat here? If we take the upper function, the big Y, and subtract it with the little y, we get for the semicircle, what is that? That's the diameter. So this diameter, the length of that diameter, since that diameter is vertical, is going to be a big Y value minus a little y value. So that's going to be, what's the top function? That's a parabola opening down. You see that S shape? So that big Y is h. That's going to be 6 minus 2 times x minus 1 squared. That's your big Y. And your little y is going to be that S shape. That's going to be your cosine function. So big Y minus little y. So we have -2, so minus -2 plus 3 cosine of pi over 2 x. That's the diameter. What's the radius then? Half that, right? The radius is going to be half of that length. The radius is going to be half of that length. So this is the radius of the semicircle. Definitely don't think, we probably could actually work all that out, but that would be an insane amount of work. So the volume of this solid would be the definite integral between 0 to 2. The area of a semicircle is 1/2 pi r squared, so there's going to be a 1/2 pi r squared dx. And that big old radius, expression for the radius is going to be big Y, 6 minus 2 times x minus 1 squared minus, oh, I didn't need much room, little y, negative 2 plus 3 cosine of pi over 2 x squared dx. Cool with that? Write but do not evaluate an integral that gives the volume of the solid formed by rotating the region R about the line y equals 6. So we're going to take this region, region R, and rotate it. Ooh, it does not do that. It just touches. There we go. Around the line y equals 6. Does our region touch the axis of rotation throughout the entire domain of interest? It touches it in one place, but not everywhere. So our solid, whatever this globulous sort of dark area shape looks like, when that's rotated around this line y equals 6, there are going to be, or will be, a hole in our solid. Is that correct? So when we make a cross section, we are going to have a circle with a hole in it. So how do you find the area of a circle that has a hole cut in it? Area the big minus area the small. So the big circle, let's use blue. How long is that line segment? How long is that radius? It's a vertical line segment, which means we're cutting perpendicular, we have representative rectangles that are perpendicular to the axis of rotation, which means we're going to be integrating with respect to x. How long is that line segment? Vertical length is what? Big Y minus little y. What's the big Y at? 6. Where's the little y at? On the cosine function. So our volume is going to be the definite integral between 0 and 2, because we're integrating with respect to x again, of pi r squared, where the outside, that should be in blue, where the outside, that radius is big Y minus little y, 6 minus negative 2 plus 3 cosine of pi over 2x, pi r squared. What function is going to define the hole? So to find the area of that hole, it's going to be another pi, so it'll be minus pi and another radius squared. That's going to be big Y of 6 minus little y of 6 minus 2 parentheses x minus 1 squared dx. Bang! All right, hope that helped. Have a great day. Sorry about the wrong.